about improper integrals, section 7.8. And an integral is improper when one or both of the limits is negative infinity or infinity. This is also known as the interval is of infinite length. So interval of infinite length. That's another way of describing that. That's type 1. Type 2 is where the function is not continuous on the closed interval of integration. Okay. So in either of these cases, technically, the integral doesn't exist in either case. It's not, a function is not what we call integrable according to most standard definitions of integrable. However, it can be convergent or divergent. So, and if it's convergent, then we can maybe evaluate it. Okay. And so that's what most of the section is going to be on determining whether it's convergent or divergent and then evaluating it. There are some problems where the objective is just to determine whether it converges or diverges and not to calculate it. Okay, now, so what happens so let me just if you're in the type 1, so let's say, for example, you're integrating from let's say we're integrating from some number, let's say 3 to infinity. So this upper limit is infinity. And so what will happen is this integral right here, if it converges, then the integral will actually be the limit as b goes to infinity of the integral from 3 to b. Or I should say that if you take this limit exists, then the integral is convergent. Okay, and it can maybe be evaluated if you can find this limit here. So the limit as b goes to infinity, this is going to infinity. So what's happening here is this right here is an interval of infinite length. From 3 to infinity is infinite length. This from 3 to b, if b is a finite number, no matter how large it is, this is a finite length. Okay, the other one, type 2, would be a function that's not continuous on the closed interval of integration. So an example of that would be you're integrating from, let's just say we're going to be integrating from 0 to 5, and we have dx over x minus 5. Or let's just say dx over x squared. So here I have the upper endpoint was the problem because it's infinity, and here the lower endpoint's a problem because when you plug the 0 in, this is 0. Okay, so the way that you would handle that one is you take the limit as a goes to 0 from the right. Okay, because your interval of integration is from 0 to 5, and so you're taking the limit as you're coming in from the right. Okay, so you're integrating smaller intervals, and that would be from a to 5. Okay, and if that limit exists, then the integral is going to exist. Now, in practice, usually you just think of plugging in that you can just evaluate. You can just evaluate it with the 0 there, and then if you can plug a 0 in, then great. If not, then it's not going to work. But sometimes you'll have to go to the limit definition. Okay, so we'll do some examples of this. So let's look at number 1. Explain why each of the following integrals is improper. Okay, this one's improper because you've got this 9 here, and when you plug the 9 in here, you get a 0 in the denominator. So that is a type 2. Okay, it has an infinite discontinuity. It's not continuous on the interval. Part B, This one is going to infinity, so it's type 1. The interval is infinite length. Here the interval is infinite length as well. So we went from negative infinity to infinity, so that's infinite length. This one, cotangent x is the cosine of x divided by sine x. Okay, and when you plug in the lower endpoint, then it gets trouble. Okay, when you plug in the lower endpoint, you get a 0 in the denominator, so it's a type 2 improper integral. Okay, so all of those were improper integrals. Oh wow. Okay. So any questions on that at this point? So once again, type 1 is where you have an infinite interval. Your interval is of infinite length, and type 2 is where it's not continuous in the closed interval. It also could be if you could also have a point of discontinuity at an interior point. And so let me just do a quick example, put a quick example of that. Let's say we have dx over the square root of x, okay? And you're going from, we can't go from -1. Okay, let's change this. So this is 1 over the cube root of x, and you're going from -1 to 1, and you want to know what the integral is. To do that one, you would go from -1 to the point of discontinuity, plus, and then 0 to 1. Oh wait, that's going -1 to 1. That's what I meant to write. And I don't know why I wrote a -1, and that looks like I'm trying to write a -1 there too as well. Okay, so if you're a type 2, but your discontinuity is on the interior of the interval, then you split up into these two. And of course, this and this both revert to this one, to this kind of a thing right here. Except here you're going from, your b is going to 0 from the left. Okay. Okay. So let's go to number 2, where we actually start evaluating some of these integrals. And usually what you can do is just like integrate it as if it's just normal, but just make sure that there's no problems in the inside here, in the interior. And if you take 7 minus 9x and you set that equal to 0, then what do you have? X equals 7 over 9, and that's not in the interval. Okay, so this interval is fine. So this is continuous on the inside, so it's not type 2. It's only type 1. So just go ahead and take the integral. And this is 1 over 7 minus 9x. So if I take the derivative of this, I'm going to get 1 over 7 minus 9x, which is right there. But I'm going to also get the derivative multiplied by the derivative inside, which is -9. So I'll put a -1/9 right there. Okay, now technically it's the limit, but I can just think of just putting a negative infinity there and a 0. If I put a 0 in, then I get -1/9 log of 7. That's putting a 0 in. Minus, and then -1/9. Now I put a negative infinity and I get log of infinity, which is infinity. So this one diverges. And that would just be the answer. Okay, just write diverges. It says to write it in all the capitals, but if you just write it in small letters, I think is also, I wrote it with a capital D and then small IVE, RGES. Okay. Okay, let's do this one right here. Number 3. Again, you're going from 9 to infinity, and so it's not discontinuous anywhere, but it's an infinite interval. Sorry. Okay, now, if you notice that the derivative of 1 over x is equal to negative 1 over x squared, so the derivative of negative 1 over x would be positive 1 over x squared. And that's just because this is negative x to the negative 1. So when you take the derivative of that, you get positive. You got a negative come down, which makes that positive, and then you subtract 1 from that, that's 2, and then that's of course that. So, and I forgot to put the dx, but we'll put that right there. Okay, so the integral here is e to the negative 1 over x. And because if you take the derivative, you'll get this, which is right there in the numerator, times 1 over x squared, which is right there. So that's pretty much it right here. Okay, and then you're evaluating out from 9 to infinity. Okay, now if you put, as you take x to infinity right here, the upper limit, you kind of get, you can think of it this way. 1 over infinity, that's going to 0, okay? That's going to 0 because 1 over, it's a negative 1 over really large numbers, and that's 0. It's like if you owed $1, if many people owed a total of $1, then each person's part of the debt would be really small. Okay, minus the lower limit, e to the negative 1 over 9. So that's minus e to the negative 1 over 9. But e to the 0 is just 1. So we get that. Okay, any questions about this? Great, let's move to the next one then. Okay, here you have an infinite interval. And you can calculate this, and we will, but you can also realize that when you're integrating sine squared, so sine squared is going to look like, okay, so hold on. So sine x goes like this, right? Forever, okay? Sine squared x then is going to be, well, it's still going to go up to 1, but it's probably going to be not as steep, probably more steep. I don't know. I actually don't know. It's going to go up to 1 though. And then it's come down here, and then, but then this bottom part is going to go up again. Okay. And so if you think about this one, and each of these has areas. So this integral here from 0 to infinity would be adding up all of these, and they're not getting smaller. Okay. And plus, if this is 9, then you know these are going to be kind of tall. Although this 9 really doesn't make any difference. So that's basically you're just gonna go to infinity. So this one diverges. And if you want, you could, if you were to calculate this out, I guess we could calculate it out, but we already know that it's going to diverge. What is that? 9. So sine squared is 1/2 times 1 minus cosine of 2 alpha, d alpha. So when you integrate that, you're going to get 9/2 alpha. And then, what is it, sine of 2 alpha? 9/4 minus that. And this one right here, this one goes off to infinity. This one, it fluctuates between, fluctuates or oscillates. Oscillates probably a better word. Between negative 9/4 and 9/4. So that the whole thing is going to go off to infinity. So again, it diverges. We get the same result. But you can also see it from the graph here that this, and then each of these has the same area and it's positive. So you're adding up infinitely many because you're just going on and on and on and on to infinity. Okay. If you have any questions, please just talk up about it. Or write something in the chat. That's fine too. Okay, number 5. Evaluate this right here from 8 to infinity. And if you look at the denominator, it's x times x plus 1. If you factor that, x times, and so at 0 and at -1, it has problems, but that's not in this interval from 8 to infinity. Okay, so you're integrating from 8 to infinity, and 0 and 1 are over here. There are points where this function is not continuous, but they're not in the interval, so we're fine. Okay. So it's not type 2. It's not type 2. It's only type 1. Okay, so this one calls for partial fractions. Like that. Multiply both sides by this denominator. And you get that. And then you strategically set x equal to different values. If you set x equal to 0, that goes away. This just becomes 1, and you have a equals 1. If you set x equal to -1, then that's negative b, that goes away, and then you have b, you end up with b equal to -1. Okay, so that means that this integral is the integral from 8 to infinity of 1 over x minus 1 over x plus 1. Okay, so you might be tempted to split it up into 2 integrals, but that would be a mistake, because then you might have one of them, you could calculate one of them to be infinity, another one to be negative infinity, and then you have infinity minus infinity, which can be strange things, by the way. It doesn't necessarily be, it's not necessarily going to be 0. And when you do limits of these things. Okay, so leave them together. Don't split it up into 2 integrals. And so I'll go ahead and integrate those. This is the natural log of x. Because x is between 8 and infinity, then we don't need the absolute values. And then likewise, when we do this one, we don't need the absolute values. Why did I put them though? Those are parentheses, not absolute values. Okay. If you plug infinity in now, then you have infinity minus infinity. So that's kind of a problem. But what you should do is use the properties of logarithms. The log of a difference is the log. Difference of logs is the log of the quotient of those. Like that. Okay, and that's going from 8 to infinity. Now, as you go to infinity, So this upper limit can be expressed this way. The lower limit, we plug 8 in. As b goes to infinity, this goes to 1. Wait, I left the log off. This inside part here goes to 1. This goes to log 1. And log 1 is 0. Okay, so the answer here would be negative log 8 over 9. Okay, and you might be, so here's one thing that's interesting. So you might be like, whoa, if you think about this, okay, you might be like, okay, over here, this function is always positive, right? This function here is always positive. So why do we get a negative number? But if you plug this in the calculator, it's actually positive because 8 over 9 is less than 1. So the log of 8 over 9 is negative. And then then multiply by negative makes it positive. You could also write it as this right here, log 9 minus log 8. That also works. Either of those forms should be accepted. I'll just circle that one. Okay, number 6. Evaluate the integral from 0 to 13 of dx over the cube root of 13 minus x. Okay, so if you plug a 13 in this function right here, and I'll write it as 13 minus x to the 1/3, because that's the cube root, is not continuous when x is 13. Because when you plug a 13 in, you get 0 in the denominator. Okay, so it's not continuous. So this means it's a type 2 improper integral, type 2 improper integral. Okay, but just proceed as if it's not. Okay, 1 over a cube root of something is equal to that something raised to the negative 1/3. You can integrate that. Add 1 to that. That gives you 2/3. Now adjust the constant so that we get this. If you differentiate this, you get this. If you differentiate this, you have a 2/3 coming down. So we'll need a 3/2 to counter that. Okay, so 2/3 comes down, and that reduces with that. This reduces by 1 power. So 2/3 minus 1 is negative 1/3. That's how we set it up. Then the derivative inside is negative 1. So put a negative 1 out here to counter that. Okay, so that is an antiderivative of this. And you want to evaluate that from 0 to 13. So first you plug a 13 in. And then subtract and plug a 0 in. So subtracting actually gets rid of the negative. And this is 0, 0 to the 2/3. This is a positive power now. So here it was negative power, but after integrating, it's a positive power. So, and then 0 to raise to a positive power is just 0. And so all we have left is just this part right here. So 3/2, 13 to the 2/3. And maybe put a, I don't think you need a times sign. I don't think you need that. So that's taken to be understood to be that. Any comments or anything? Okay, let's move on to number 7. Okay, with this one, this one is a problem. It's a type, it's the function e to the 1 over x cubed is not continuous at x equals 0. It's not continuous at this lower endpoint. Okay. So that means it's type 2 improper integral. You also have another challenge is that another challenge here is that there's no antiderivative of this. Okay. Okay. And so this is another problem, or we'll say issue. Another issue is that e to the 1 over x cubed, it has no antiderivative. In closed form. Of course, everything has an antiderivative. Well, everything that's integrable has an every expression has, I suppose, has some antiderivative. It's continuous on whatever. So there is some antiderivative, but it's not anything that we know. It's not any function that we know. Not anything we can write down, and let alone evaluate from 0 to 1. Okay. So sometimes that would mean that we can't do the problem, but the problem says determine whether the integral is convergent or divergent. If it is convergent, evaluate it. So if it's convergent, then I don't know how we would be able to evaluate this. But luckily, it's actually divergent, and you can actually show divergence this way. Here's how you can show. Here's what happens. Okay. So if let's suppose that f of x is greater than or equal to some other function g of x on an interval. Okay. Okay, now, so you have f of x. So this would be our f of x, right? This is our f of x. Well, there's like actually, I should have wrote a 39 there. Dang, I was just like taking stuff out. Okay, so if our function, well, in this case it's this function, is bigger than some other function on the interval from a to b, and that other function diverges. Okay, so in other words, if we can show this function is bigger than some other function, and that other function diverges, then this function also diverges. Okay, if this diverges to infinity, not just diverges, but diverges to infinity. Okay, because you could have a function that I'll give an example of that later. Okay, so but anyways, so what's going to happen? So the way that we can attack this is we can use this principle here, and I'm going to let g of x be 39 over x cubed. Okay, so the thing is, okay, so note this, that if x is between 0 and 1, then e to the 1 over x is greater than or equal to e to the 1, which is e. Okay, which is greater than 1. So that means that 39 e to the 1 over x is greater than or equal to 39e over x cubed, which is going to be greater than 39 over x cubed. Okay, so the g, this g satisfies all this right here. Also, if you take the integral from 0 to 1, 39 over x cubed, okay, that's integral from 0 to 1 of 39x to the minus 3. And you integrate this, you're going to raise this by 1 power, so the minus 2. Okay, and then adjust the constants. So when I take the derivative here, I get a negative 2 coming down, which knocks that and that out. And this reduces by 1 to a negative 2 minus 1 is negative 3. This is negative 39, negative 39 over 2 x squared. From 0 to 1. I could plug a 1 in, but when I plug a 0 in, this is going to go to infinity. That's finite. This goes to infinity, so the whole thing's infinity. So I satisfy that part. Okay. So here, so this side, this part right here satisfies that part. And f is bigger than g. Our original function is bigger than that one. So therefore, this original integral diverges. And then just put that as the answer, and we're done. Okay, great. Let's do another one, number 8. So I like, when you have like written as radicals like this, I like to rewrite it in the numerator with a power. And the power is negative 1/3, like that. Okay, if we plug a 0 in, we have 0 minus 1 to negative 1/3, right? And that's fine. If you plug a 9 in, that's fine also. But what you have a problem with is plugging 1 in. Okay, so to the function is not continuous at x equals 1 at 1. So you plug a 1 in, it's not going to work. Okay, so what you do is you split it up into integral from 0 to 1 of 9 x minus 1 to the negative 1/3 plus integral from 1 to 9 of the same thing. Like that. Because it's not continuous at 1. Plugging a 1 in here gives a 0 in the denominator. And 1 is in this interval here. Okay, so here is 0. Here's 9. You're integrating across the interval. At 1, you have a problem. Okay? It makes this an improper integral. So we split it up like this across. You're gonna go from 0 to 1, and then from 1 to 9, like that. You split it up into 2 integrals like that. Each of these are improper integrals, and they're type 2. This original one's type 2. Now we have 2 improper integrals that each are type 2. But the problem is that the discontinuity is at the endpoint. Is at this endpoint 1. Okay, so you integrate this. Let's see here, x minus 1. Add 1 to that, you get 2/3. If you differentiate this, you're going to have a 2/3 come down to, so 27/2 should not know that. So when the 2/3 comes down, the 2 will cancel with that 2. The 3 will, this 3 will be down here. It will reduce that to a 9. And then the derivative side is just 1, so don't have to worry about that one. Okay, and that's being divided from 0 to 1. And then this is the same thing, or like the same antiderivative, not the same definite integral because it has a different limits of integration. It goes from 1 to 9 this time. Okay, so put in a 1, and that's nice, you get 0. Subtract and put a 0 in. When you put a 0 in, you get negative 1 to the 2/3, but you do the square first, and that becomes a positive 1, and the cube root of positive 1 is positive 1. So it's just negative 27 over 2. And then you put a 9 in. So you got 27/2, and then you have 9 minus 1 is 8, so that's 8 to the 2/3. Subtract, put a 1 in. When you put a 1 in, that's 0. Look at that. So negative 27/2 plus 27/2 times, let's see, 8 to the 2/3. So let's do the cube root first. That'll give us a 2. 2 squared is 4. So 4. So basically, we have 4 of these 27/2 minus 1 of these 27/2. That means we'll end up with 3 of these 27/2, which is 81 over 2. Okay, now if you didn't see this, that it's not continuous at 1, and you were to integrate this, not even seeing that, then you get the same answer this time, which is kind of strange, but that's not always going to be the case. Okay, so for example, if I integrate from negative 1 to 1 of dx over x squared, for example. Okay, so this is like typical problem that they would put on in like a graduate school placement exam or something. They just try to mess you up. Here it has a problem at 0, right? So you'd have to split up into 2 integrals. That's x to the minus 2 dx plus, and then 0 to 1 is x to the minus 2 dx. And when you add 1 to that, you get x to the negative 1, negative x to the negative 1. And then when you plug in, so that's basically negative 1 over x divided from negative 1 to 0. And then right there, when you try to plug that in, it's just not going to work, okay? So this one diverges. And the other one's also going to diverge. So the answer there would be that it diverges. Okay, this integral diverges. But if you didn't realize that, then you could fall into this trap right here. So this would be wrong way to do it. And you could just be like, oh, okay, it's negative x to negative 1, divided from negative 1 to 1, or negative 1 over x divided from negative 1 to 1. You put a 1 in, you get negative 1, subtract, and put a negative 1 in. Also, you get like negative 2. Okay. And this is a completely wrong answer, because you could even, like, if you look at the original one, every single value here is positive. Okay, when you put an x between negative 1 into here, it's positive. So your integral has to be positive. But here you get negative 2. It's because you have a discontinuity in the middle. Okay, so this is wrong. That's the wrong way to do it, and you get a wrong answer, and then you're sad when they find out that it's wrong.
So when
another thing, yeah, go ahead.
So when something converges, does that give you a numerical value, or how will we know when something's convergent?
Here's what you can do. So you don't necessarily have to, you can use this, okay? If you have a function like this, but everything's positive though. If you have this right here on an interval from a to b, and this integral right here converges, then this integral here will converge. Okay, so here's a situation where you don't necessarily have to calculate the integral to know that it converges. And it could be a situation where you can't calculate the integral, or at least not in closed form. You could do the methods from our previous section, perhaps. But then again, maybe not, because maybe not. Maybe that would not work very well, because if you had, yeah, that might not work. Yeah, that could not, yeah. You might have a lot of trouble using the methods from the previous section, even though you'd know that it converges. So if it's an improper integral, because it could be like, if it's type 2, at one of these endpoints, it could blow up to infinity or negative infinity. Or not infinity, because we're saying it's positive. So it could blow up to infinity at one of these endpoints, and then when you try to use numerical method or approximate integral, then it messes you up that way. So I don't know, man. Okay. And then one other thing that I wanted to show you is that, and maybe I should give you an example of this first. So an example would be something like, like the integral of from zero to 1 of cosine squared x over the square root of x. Okay, this is something you can't integrate it, but you know that it has a problem at 0, because when you plug a 0 in here, it gives you a 0 in the denominator. When you plug a 0 in here, it just gives you a 1. So this is something that you can't integrate. Okay, so this is when you can't integrate. But cosine squared over the square root of x, that is less than or equal to just plain old 1 over the square root of x. Okay, so this integral here, and it's always positive, right? It's always positive. This is always greater than or equal to 0 on the open interval. But it's less than or equal to this function right here, and you know that this guy right here is x to the minus 1/2, and you integrate that, you get it's 2x to the positive 1/2. You plug the limits of integration in, plug a 1 in here, you get 2 times the square root of 1, which is 2, minus, plug a lower one, you get 0, you get 2. So that integral is 2. So therefore, this original one converges. Okay, but we don't know what it, but can't evaluate it. Okay, we know it's going to be less than or equal to 2, less than 2 for sure, but we don't know exactly what it's going to be. Okay, and this is what I've basically showed you here. This is called comparison test right here, as well as this one right here is the comparison test also. And these are both kind of really from the same kind of test. You could argue that these are pretty much equivalent to each other. This comparison test and this comparison test, which is used to show that something converges, and another one should use to show that something diverges. There are other tests, but we won't get into that for now, at least. And then there's another case where if you had, like, let's say you integrate from 0 to infinity of just sine x dx. This one right here, because sine x goes like this. This one diverges. Okay, but not to infinity or negative infinity. Because what this is it's the limit as x as as b goes to infinity of, okay, if I take the antiderivative of here, I get negative cosine x from 0 to b. And so that would be the limit as b goes to infinity of negative cosine b. And then if I put a 0 in, I get plus 1. And so this right here oscillates from between -1 to 1. Okay, this right here. So depending on, so if you think of this as being your b, that could be a value of b. If that's the value of b, then that and that are going to cancel each other out, and this is going to cancel part of that out. So you'll end up with just like, be this much right here. But if this is your b, then that and that cancel each other, and that cancel each other out. So you get 0. So your integral from here to here is 0. Okay, integral from here to here would be you adding another part, another hump right there, would be this, the area under this hump here. which I believe is 1, if I remember correctly. So it's going to be different values as you're moving along, as you're coming out this way. So it diverges but not to infinity, or negative.